All right, I think I'm going to get started with the introduction so that we have a little extra time for questions if need be. Does that sound okay, Kwan?
Yeah, of course.
All right, great. Um, Awesome. So, hi everyone. My name is Dinesh Jairaman. I'm an assistant professor at the University of Pennsylvania, and I'm one of the co-organizers. And it's my great pleasure today to host our morning speakers. Morning, I guess, depending on which part of the world you're in. And we're delighted to have as our first speaker, Professor Andrew Davison, speaking on the topic of representations for spatial AI. Andrew directs the Dyson Robotics Laboratory at Imperial College London. And really, over the last 2 decades, Andrew has been responsible for some incredibly seminal work in SLAM and active vision. And over the last few years, he's also been moving towards combining the geometry insights from his earlier work with semantics into spatial AI, which is also the title for this talk. So Andrew is a fellow of the Royal Academy of Engineering. He's won numerous Best Paper awards. He's also translated his work into the Dyson 360i vacuum cleaner, and he's recently started a startup called SLAMcore to improve chip design for SLAM. So with that, I'll hand you all over to Professor Andrew Davison.
Thank you very much. Yeah, it's very good to be here. So yeah, that was a really nice introduction. So hopefully by the end of my talk, you'll understand what I mean by this title, Representations for Spatial AI. But yeah, my career has really primarily been in this area of visual SLAM, so localization and mapping with vision as the primary sensor. And having worked on that now for a number of years, it's exciting to see that you can actually buy products that are equipped with these capabilities. So these are in several areas, and certainly my primary interest was always robotics, and some of these you would certainly call robots, like the Dyson robot vacuum cleaner. There are other robot vacuum cleaners that also do visual SLAM. There are drones from companies like DJI or Skydio that have really sophisticated visual SLAM systems, but there are also other quite different products that do very similar sorts of things in terms of visual SLAM, but you wouldn't necessarily call them robots, like AR headsets or like SLAM on smartphones. What these products really do so far, they have some primarily, very high performance sparse local mapping that enables accurate positioning, usually with sensor fusion of vision with possibly some other sensors like inertial sensors, and also emerging as some level of dense and also semantic mapping. So this is one way of thinking of that. So levels of performance in SLAM that are gradually building up localization, mapping, and semantic understanding. But just to understand what I mean by this term spatial AI, so I don't necessarily think of it as, SLAM is a layer and then spatial AI is something that sits on top and enables all the really cool intelligent stuff. For me, I think that's what I've always been interested in. It is, methods that can enable intelligent devices and products that can actually do useful things. I feel like that's what I've always been working on, and now maybe spatial AI is a more appropriate label for this whole SLAM project, which is gradually evolving, I think, to encompass more and more. So the particular character of SLAM has been in particular focused on real-time incremental operation, real kind of demoable systems that have efficiency built into them. So most advances in SLAM have been represented by a real-time demo downloadable code. So it's quite sort of systems based, and I think we need to retain that systems based thinking, a focus on real-time and efficiency as we move up these levels and expect more and more from spatial AI. So where might we get to eventually? Maybe really ambitious sort of products, and this is just a picture that doesn't represent any kind of real concept, but maybe a very general home robot that could do all sorts of different things, like tidy up a kitchen, for instance. Or interestingly, I think it would also enable this, so a really kind of general purpose augmented reality system that could do all sorts of things for you, to get together with the human that's wearing it, but come in under very strong constraints of very lightweight and very long battery life. So, one of the key points I'd like to make is I think we have a long way to go to get to these really advanced products. And I think especially when we consider the very strong constraints that they would have to fit under. So we've got the current products and the capabilities they have. We've got work going on in labs and current research prototypes, which kind of cross this large chasm. But I think we need orders of magnitude of improvement to get to where we really need to enable products like that. So that's what I'm interested in working on. I've thought about this in general quite a lot, really. There's a couple of papers I've written recently called Future Mapping. There's two of these so far, one and two. The first one in particular, we're thinking about the general concept of spatial AI as a sort of computational system. So what are all the things that we would actually need to do computationally in spatial AI, and how might that all fit together, and what might the actual eventual path be towards making it efficient? And there's a number of hypotheses in that paper. Probably the most significant one is that there's a generality to these type of systems, which would be useful for many applications. So one of the projects I've been involved in recently, which I think is trying to push research in this direction. This is a paper you might have seen called Rearrangement, a Challenge for Embodied AI, which I was working on together with a really interesting group of people. So this is thinking about simulators, so embodied AI, robotics simulators, and the kind of challenges that they might present in order to try and drive really interesting research. And we came up with this class of problems called rearrangement, which we think has general properties. So a rearrangement task could be, for instance, tidying a kitchen, but it could be all sorts of other things where there's a set of objects that need to go from some initial locations to some goal locations. And we in this paper discuss things like, how would you specify a task like that? How would you evaluate whether it's been successful? And I think that's driving research, hopefully, towards what I think is important, which is persistent, real-time, updatable compositional scene representation. So although a lot of this work kind of in simulated challenges for navigation and so on so far has really, I think, encouraged work on sort of end-to-end learning approaches, for instance, for navigation to some location in a space. I think that the kind of tasks we're talking about in rearrangement will not be feasible, or at least not for a very long time, with approaches anything like that. Because think about tidying a kitchen. You have to sort of recognize a whole load of objects. You have to think about where they are. You have to move repeatedly around a space. And I think you need something like a representation, a map of that space in order to tackle tasks like that. So most of my research is on what are the kind of representations that I think would actually enable capabilities like that. So just to mention, so that paper talks about several simulated environments that people can actually download and play with if they're interested in this, including one called RL Bench, which comes out of our lab at the Dyson Robotics Lab, which is a benchmark of robotic tasks in a simulator, focusing on wide variety. So there's many different sorts of tasks that you can try with the same robot setup. Okay, so let's start talking about representation. And so obviously something everyone's been thinking about is how do how do all these methods we've been designing over the years meet with what's now possible in deep learning? And this is obviously something I've had to think about a lot recently. And my position is that I think there's really a sliding scale between fully end-to-end learn algorithms, which are represented by a single neural network that will sort of take images and output robot actions, and at the other end, some kind of fully human designed algorithm along the lines that I and many others were working on until a few years ago. There's a sliding scale between here where you can design systems that have any combination of these two elements. And I think that pretty much all of us that are designing pragmatic systems now that we expect to actually be useful in anything like the near term are looking at various positions along here. So how much of a system do you design? Do you design the main component of the system, the sort of structure, and then the parts that are hard to design you replace with neural networks that you train? Or do you start with a neural network and you then put lots of structure into that to represent various things that you know, priors and design? I think in the end, those two approaches may not be that different. But what are the right kind of choices to make? So for the rest of the talk, I'll tell you about some of the things we've been doing in our lab, which I would say lie somewhere along this sliding scale. You know, we're interested in, you know, understanding rooms, scenes, objects, and you know, in particular, I'm focused on indoor robotics due to my work with Dyson. You know, how can we make use of neural networks that can do surprising things? So neural networks, it was always quite clear that there were things that they could do that we had no idea how to do very well before in computer vision, like object recognition, for instance. Well, saying no idea would be wrong, but you know, neural networks came along and immediately did better at things. You know, once they were scaled up to the right level, like image classification or segmentation than you know, previously designed approaches. But probably what surprised people like me more were when they started to encroach on more geometric vision, so doing things like pose estimation or depth prediction. I would say that's interesting because they still haven't necessarily, you know, blown away all previous work in areas like that, and they're still, you know, still the best sort of pose estimation systems and you know, SLAM and structure for motion and so on. They're largely hand designed systems at the moment. But anyway, so let's consider in this. So we had a paper called CodeSLAM, where we were really trying to think, you know, there are neural networks that are pretty good at predicting depth for a single image. How can we actually use that in a system where our goal is to build a persistent representation of a room? So in particular, when you have you know, two overlapping views, each of which you've got a depth prediction for, and you may be able to, you know, also estimate the motion of the camera. How do you actually fuse those multiple depth predictions into the best 3D representation you can? And something that doesn't necessarily work very well is just sort of, you know, take those overlapping depth views and somehow average or fuse them in 3D. And that's particularly because, you know, the predictions you get from a neural network, you know, they will have errors in them, and they will have errors of a pattern that's actually quite hard to characterize. So it's actually hard to come up with the, you know, a distribution over the uncertainty in those sort of predictions from a network, and therefore it's hard to fuse them. So in CodeSLAM, we used a different sort of approach, which is where we have a depth prediction network, which is attached to a variational autoencoder, which gives us the ability to then use a small code to control the prediction. So apologies, this is a bit of a complicated figure, and it shows a bit more than that, in fact. But really looking at the bottom part of this, you've got an image coming in, it passes through a network, you get a depth prediction out, but then you also have access here to a code. So this is a small vector of about 32 numbers, which are basically sliders that when you change those parameters, it changes the depth prediction in ways that are consistent with the data set that you have trained it on. So this means when you do multi-view fusion, rather than needing to average the depth predictions, what you do is you optimize the two codes for your two overlapping views to generate depth views that are consistent, but they'll be consistent in a way which is consistent with what's in the data set. So I'll just show you an example of our kind of later extension of that. So we realized that you could use the same idea as in CodeSLAM, which is about depth prediction, for semantic prediction. So in CodeSLAM, we have a network which goes from images to semantic label predictions in an image, but then also gives us these codes that we can optimize. So if I just show you this example here. So this is running here on a couple of synthetic images for which we have ground truth. So these are input images. These are the ground truth semantic labels for those images. And these are what we get in this third column here, the semantic predictions just from a sort of passing those feed forward through a network. But if you imagine now trying to combine these two semantic predictions, you're not necessarily going to get anything very good just by averaging these pixel by pixel. And when I say pixel by pixel, I mean with geometric alignment taken into account. So we do know the camera motion between these frames. So look at this one here, for instance, at the bottom, the semantic labels for the table are quite poorly predicted, because we're not seeing the whole of this table and it's quite ambiguous. It's just a big flat thing and we don't really know whether it's floor or table or wall, for instance. But what we do in scene code is we adjust the two codes here to try and minimize the semantic error. So the semantic error here is basically the difference between the two predicted semantic maps, where, having been geometrically aligned. So you can see there's a big error here, particularly on the table, and then this kind of area over here at the back. But when we then start optimizing the codes to try and minimize the semantic error, you'll see the predictions gradually going closer and closer to each other. So we are actually able now to get really nice, solid predictions for this table at the bottom here via code optimization. There's another small example, which I'll just show you here. So in this one, we've got 5 overlapping views. And there's the interesting situation in this one where we're making predictions for this scene, and in the third column here, you can see there's this tall sort of object here on the right. It's pretty hard to label this accurately. Clearly, if we just averaged these labels pixel-wise over these views, we're not going to do much better than the individual views. And there are places here, there are pixels here where none of these images have the correct label. But when we do code optimization, we're actually able to really fix that problem and get really nice semantic label predictions for all of the frames, because in our data set, this is what we see. We see big coherent objects. Okay, so that's CodeSLAM and scene code. If you're interested in those kind of methods, by the way, I'd recommend having a look at our project called Deep Factors. So this is a full kind of code release that actually runs in real time and embeds the CodeSLAM idea in a general probabilistic factor graph framework that performs quite efficiently. But one of the weaknesses of an approach like that is it does rely on a data set. So in fact, the images I was just showing you there, that's a synthetic data set, a rather old one now that out of our lab called CNET RGBD, which we train that network on, and it works really well on images from that data set. It also does work somewhat well on real images, and if you look at the videos from that paper, you can see it working on real video. But it's very much a problem that we have found, especially in indoor scenes, where I think it's really hard to get a wide variety of real data. And whenever you train something and bring a camera into your own house and just move it around, it's usually very disappointing how well it works. So I think methods that use more sort of unsupervised learning and actually really learning specifically in the scene that you're going to use them in are incredibly well motivated. So that's one of the things we've been working on recently, really networks that you train specifically for particular scenes. So we've got a project we recently released called IMAP. So this uses an implicit neural representation to represent a scene such as a room from multiple views. So it's very similar to NERF and things like that in the sort of representation it uses. It's a single general multi-layer perceptron using this kind of setup where you feed in a coordinate and it will output properties of the scene at that coordinate, such as scene occupancy and color. But we show that you can actually train a representation like that in real time as a camera moves around a scene. So let me just show you the video. So the first thing to say that's different from NERF is that we are using here a depth camera rather than an RGB camera, and that's something that makes this a lot easier. And we haven't yet, got anywhere close to doing this in real time without a depth camera. So we've got a depth camera moved in real time around a scene. So it's capturing a sequence of RGB and depth frames. And then what we're doing is optimizing this implicit neural representation continuously against this growing set of data. So we don't use every single frame that we've captured. We gather a set of keyframes, which we think spans the scene. You can see those keyframes at the bottom here. And in the top right view, you can see the kind of red shapes here that represent the estimated positions of the keyframes. What we're trying to basically optimize is to try and make it so that the rendered views from those keyframes, so when we render into the implicit neural function to get out a depth scene and an RGB scene from a particular camera position, we then want to minimize the difference between those rendered RGB and depth scenes and the actual RGB and depth that we have captured from that position. So we treat this as a full SLAM problem in that we also optimize the positions of the camera via this rendering process. So there's no sort of separate sparse SLAM system or anything here. It's all done through this implicit network and a full joint optimization. So yeah, that's how the system works. And you could see there that, so this does run in real time, and within 3 or 4 minutes, we go from this, very sort of blurry and piecewise sort of representation of the scene towards something here that now looks quite compelling. So it's not yet super accurate, but it's very good at capturing the main structures and volumetric elements of the scene. What you can see going on at the bottom, this kind of flashing around and these dots, this is actually a sampling process. So this is, again, all about making this fast. So we don't present the data with all of the network, don't present the network with all of the data all of the time. We sample both from the keyframes and within the keyframes of pixels to actually use for a training signal for this network. But this has all the nice properties of an MLP in that there's nothing here defining the resolution of our scene. When we go closer to objects, we can capture them in more detail. And actually, one of the nice points is that this is a really very kind of compressed representation of a scene. So actually, it's quite a small MLP we're using. There's only about a megabyte of weights involved here. So actually, one of the things that led us to think is, if this network is so good at compressing the scene, it's probably doing it in a relatively object-aware way. And in fact, you can see some kind of clues into that. So if we go back to watching this as it's actually optimizing, and you see the whole scene kind of wobbles a bit as the SGD training happens. And if you look at something like this is a football on the floor down here, what I always found interesting was that the whole football kind of wobbles quite coherently. So the whole football tends to either get bigger or smaller, for instance. So what that really led me to believe is that there are relatively few weights in the network that are actually involved in generating the shape of this ball. So that means, in my mind, that the network has really learned to decompose the scene in quite a smart and fully unsupervised way. So that's one of the things we've really been investigating further recently. And just to show you this paper, so the paper is actually called In Place Scene Labeling and Understanding with Implicit Scene Representation. We've really been investigating what happens if you add on to this NERF-like implicit network that takes in coordinates and outputs here, it would output color, it might output density. What if you also add a semantic output? So right at the end of the network, you give it the ability to also predict semantic properties of the scene. The fact that this network has sort of been self-supervised in terms of color and shape to learn a representation, which we think is getting something close to the sort of object-like structure of the scene, the semantic output should also inherit that. And we tested that, and it definitely does seem to be true. So some of the applications that kind of allows are, for instance, what if you've only got very sparse labels. So I'm really thinking about, using this, for instance, you bought a new robot, you've brought it into your house, it's built a kind of representation of your scene like that. And then you would like to give it semantic labels, but you would like to give it very, very sort of sparse semantic labels. So for instance, just point to a few things in the room and tell it what those are. This sort of representation does enable that. Or some of the other things we tried, you can give it very low resolution labels, or you can even give it very noisy labels. So I think I'll just skip forward to the part here where we give it very sparse labels. So what we're doing here is we've trained this network in a scene. So this is showing it here on one of these replica scenes. So we're giving it the full kind of RGB information here, but we're only giving it this very, very sparse semantic information. So this is something kind of equivalent to a human who's been in this scene and is just clicking in a few places. It's able to successfully propagate those labels densely to the whole rest of the scene in really quite compelling ways. So we think this is a really interesting route to very, very sparse annotation for semantic labeling. Okay, so I'm pretty much coming up to time now. So I think I probably won't have time to show you too much more, but let me just show you one more video here. So that was all about kind of representations of whole scenes. Another kind of key area we've been investigating is more specifically object-based representations of scenes. And our latest work in that direction is this system where we used learned class level deformable shape models to represent objects. So here you can see that we've got, bottles, mugs, bowls, and cans in a particular scene. Once we've detected instances of those objects, we fit these shape models to them. And that can work really quite flexibly and at scale. And essentially, we build a representation of a scene which is like a SLAM map, but where the entities of those map are objects, and where we jointly optimize camera pose, object pose, and then these object codes that determine their shapes. And I'll just show you this part here, which is what we can actually do with that, which is very exciting for me in the context of this rearrangement type of tasks. So here we show a tidying operation. So a lot of the work you might see in robot manipulation is just all about grasping objects and then dropping them somewhere. But if you want to actually place objects precisely, I would strongly argue that motivates a really quite precise 3D understanding of what those objects are and what their shape are. So that's what we're able to get here using this method, and then we're able to do this very precise manipulation. So we've never seen these particular objects before, but we're able to pick them up. So here we pick up the bowls in size order from biggest to smallest, and we're able to stack them very precisely in the box here. So the kind of planning and manipulation part here is just some off-the-shelf planning stuff, but the tricky kind of perception part has been solved by our object-based SLAM system. Okay, so I'd better finish there. So just to conclude, spatial AI research, I think it's exciting, and we're going to be doing it for a long time yet. And yeah, these are what I think are some of the most interesting research directions. So I'll finish there. So thank you very much.
Thank you very much, Andrew. And I want to remind the audience that if you have questions, you can raise your hand or post them in the chat, and then we'll get to them. Meanwhile, I can get started with a question to Andrew. So I really connected with something that you said at the very beginning of the talk, where you spoke about how in vision, really one of the fields within vision that has for very long been aware of the requirements of putting vision systems on robots is the SLAM area, right? And in SLAM, there's always been this consistent emphasis on system building, on real-time performance, on being aware of other cost functions, like potentially energy and so on. So I wanted to kind of, as an insider into vision more broadly, to get your take on sort of what you think, or do you think that we should be thinking about these things in other parts of vision aside from SLAM? And what are your comments on that in general?
Oh, absolutely, yeah. And I think that we've drifted away from that, and there's far too much work which is just about data sets and benchmark beating, which has lost sight of the big picture. I think that system building is really crucial, and I still think I can learn more about an algorithm by playing with a real-time demo for 30 seconds than I can from any amount of benchmark results. So yeah, and then the aspects of work that really drives you to, like for instance, what classes of algorithms are actually worth investigating, because they might actually one day be feasible to run efficiently in real time on the hardware. And that's another big area of my work, which I didn't get to talk about today, is the kind of interaction between algorithms and the hardware that they run on. So that could be sensor hardware, but particularly importantly, processor hardware. And we've been riding Moore's law for a long time with CPUs. That's come to a halt. We've got GPUs, which have been very useful for a few years, but I think that's also just a beginning of where processing hardware is going. And there are exciting new things coming along, like graph processors, which might enable massive parallelism, but with quite different sort of computation patterns. So those are things that I think about a lot. We've got these quite complicated systems, but how can we actually ever put them together to really enable problem solving and products?